Okay, let's talk about logarithms, right? We'll talk about the definition, we'll do the graphs, and we'll play around with, I don't know, some expressions of logs. Okay, so let's talk about powers. Let's say I have 32 equals 2 to the fifth, right? Which 32 does equal 2 to the fifth. But instead of the large number 32, what if I wanted just to represent this as the power? What if I just wanted to say, I don't want to do 32 because 32 is too big. I want this, I don't know, my value to be the power itself. So in our previous work, right, I made this weird symbol, right? And there's nothing wrong with this, right? What if I said, hey, look, anytime you see a number as a subscript and then a large number and then equals another value, this means that the subscript to this power is the inside, right? Nothing wrong with that. But then you can see that this weird notation, I actually get the value of that notation is the power, right? So I have an idea here where the actual value of this function or this thing I'm making up is a power. So what if I even labeled it instead of just doing this weird notation? What if I told people, hey, this is that weird power thing that I'm going to do? So it's this weird power thing. And when you see the two as a subscript and the big number, then this means that two to this power, because this whole thing equals the power, and that's the whole point of this, right? Is that 32? Well, that's not so unusual. So in fact, this is what they did a long time ago. So, and they use the Greek terms, right? Logos for ratio and arithmos for number to combine those two to come up with logarithms. So instead of power thing, they call it a logarithm. And a logarithm simply is just that idea. It tells me the base that I'm going to raise this to get this inside. So now the actual value of this logarithm is an exponent. So now, for one thing, too, we don't write logarithm. That's way too long. So we shorten it to just log. So if you see log base 2 of 32 equals 5, keep in mind that the value of this logarithmic function, right, this log function is an exponent. That's the whole point of this, okay? All right, so having said that, let's take some notes. So the first thing is a logarithm is simply just the inverse of an exponential. It takes our exponential, and the value of a log is that exponent, right? So remember, so log base a of y, that equals x, but x is a power. And in fact, the power is on this base. So if log base a of y equals x, that means this is true if and only if a to the x equals y. All right, so logs are simply just ways to represent powers. Well, the values of logs are powers. So now we can actually kind of represent, we can use our number system as a power system. So it's just exponents, right? So that's what logs are kind of all about. And there's wonderful uses for them too, which turns out to be kind of cool. All right, so a couple things to note. In my log notation, a has to be positive and y has to be positive. So neither one of those are negative. All right. And then also note that the value of logs are exponents, right? That's the whole point of this. So if I have something like log base 2 of 8 equals 3, it means this log expression equals 3, it means that it equals a cube, right? So when you see log equals a number, that's an exponent. So this means it's a cube. So log of base a of y equals 5 means it's the fifth power. This is a power of 5 as an exponent. Okay, so again, the value of logs are exponents. They're the powers that when I raise this base to that power, I get this inside number. Okay? All right. So let's talk about this first. So why do a and y have to be greater than 0? Well, let's start with the a. So remember that log base a of y equals x is just the inverse of exponential. So this is true, or this is true if and only if a to the x equals y. Right? Well, if that's the case, then let's pick an a. Let's say a is less than 0, which means negative. Let's say a is negative 1. Well, if a is negative 1, this would be log base negative 1 of y equals x. Conversely, this is true only if this is true. So let's make a negative 1. Well, I'll get negative 1 to the x equals y. And now, do we have any problems? Remember that x can be any number we want. It's a variable. So let's pick a half for x. Right? If this is true, it needs to work for all x's. So let's pick a half. Well, what's negative 1 to the half? Negative 1 to the half is an imaginary number, right? It's I. Because, right, a 1/2, remember our rational exponent is really a root, a radical. So negative 1 to the 1/2 is the same thing as square root of negative 1, which is I. All right, so there. I can't have negative a because anytime I have a rational exponent with an even denominator, I'm going to come up with an imaginary number. So a can't be negative, right? Well, there are certain a's that work, but we can't say, hey, look, a can only be negative sometimes. It doesn't work like that. So instead, we just say, hey, look, a is always positive, and then you'll never run into this issue. All right, well, if a is always positive, then remember the log is true if and only if this is true. So I'll have a positive number to the x, and any positive number to the x will always be positive, right? Pick a number and raise it to a power. It doesn't matter what power you raise it to. If you raise it to positive powers, it'll be positive. If you raise it to negative powers, it's reciprocal and still be positive, right? So the fact that a is always positive, when I raise it to x, it means y will always be positive. All right, so y is always positive by default, right? It's only because a is always positive. All right, so let's try this. I want to convert each log to exponential form and each exponential form to log, or each exponential to log form. So here I have 5 squared equals 25. Remember, a log is, we want to write an expression such that the result is this power. So remember, log base a of y equals x is true only, or if and only if a to the x equals y. So in this case, a is 5, x is 2, and y is 25. So log base 5 of 25 equals 2. That's how I'd write the log expression, other than the log form. Okay, so now 2, this is already in log form. So look, we have base of 3. Remember, logs equal powers, so this has got to be 3 to the 4th, and then equals 81. All right, so there we go. So that's taking log form into exponential form. Okay, so let's stop this. So you want to do classwork problem number 1. Okay, let's try another problem here. Let's say I want to evaluate this log. So, and this log in log form, right, logarithm form. So log base 8 of 64. Right? Well, we can already tell that we want to figure out 8 to what power equals 64. Well, 8 squared is 64, so this expression should equal 2. Right? But let's say that wasn't this easy. Well, how do we do it? An easy way to do this is just to say, hey, log base 8 of 64 equals some number, and my job is to find that number. Well, it's in logarithmic form. Let's change it to exponential form. So remember, base, logs are powers, so base to this power equals the inside. So 8 to the x equals 64. And we solved a bunch of these, so just get common bases. So either turn the 8 into 64 or the 64 into 8. So I know that 8 or 64 is 8 squared, so I'm going to change the 64 into an 8. So if the bases are the same, 8 to the x equals 8 squared, then x has to be 2. So I know x is 2. If that's true, then that means x is 2. So log base 8 of 64 has to be 2. And exactly what we thought, right? So it's a nice check. Do 8 squared equals 64. Perfect. Okay? All right. Okay, so stop this and you want to complete class or problems 2 and 3. Okay, so now what we want to do is actually graph y equals log base a of x. Now recall that, first of all, logs are inverses of exponentials. So log base a of y equals x is the inverse of y equals a to the x. So remember, not a long time ago, but before we did our inverses, right, we solved this for the input, right? So we would solve this for x. So this would be x equals log base a of y. And then we did that weird thing, remember, so we could graph them on the same coordinate system. We just took all the y's, made them x's, and all the x's and made them y's. So that's how this inverse turns into y equals log base a of x. We did that trick where we really solve for the input, but then to make them so we could graph on the same thing and work with them together, we just changed the x's and y's. All right? Okay, so we really are graphing the inverse. We're just doing that little trick. All right, also remember that an inverse just switches x and y, right? So we're going to, this is y equals, or we're going to solve for x equals. So we just switch the independent and dependent variable. That was nice. And then remember, inverses also are symmetric over y equals x. That'll help too. So why don't we graph y equals a to the x? That's a simple exponential, right? As x gets smaller and smaller and smaller, then a is going to get smaller and smaller and smaller and go to 0. And as x gets larger and larger, then a will get larger and larger. Okay. I didn't really state it, but I should have. This is true for when a is bigger than 1, right? So I didn't really write that, but this is our general exponential. All right. Assuming that a is greater than 1. Well, if that's the case, well, all I have to do is draw a nice little line of symmetry and then change all the x's and y's, right? So you can see it hugs the y-axis, or I'm sorry, the x-axis at negative x, which means my inverse will hug the negative y-axis. And then my exponential goes to a positive y, so my inverse will go to a negative or a positive x, right? And you can see they are symmetric about y equals x. That's that line right there. And here's the point, 0, 1, and now we have 1, 0. All right, so this is the actual graph of y equals log base a of x. Okay, and again, this is, I didn't write it, but this is a graph for a is greater than 1. All right, okay. All right, so let's try this. Let's graph y equals log base 5 of x. So we already know the shape, right? It's going to look like this. It's going to hug the negative y-axis, go through 1, 0, and then kind of follow out to the positive x-axis. But let's just do it, I don't know, let's do with some points. Let's show that if we plotted or did a table, we could just plot these points. All right, so remember, y equals log base 5 of x is true if and only if x equals 5 to the y. So let's do a table. And here's where I find it easiest. We're going to graph y equals log base 5 of x, but instead of plugging in the x's, let's do the y's because this one's really easy to figure out, right? So remember, this is true if and only if this is true. So we can work with either one, but it's easiest, I think at least, to use this exponential. All right, so I'm going to do my y's. Easy to do, just negative 1, 0, 1. And then I'll do 5 to the negative 1, 5 to the 0, and 5 to the 1. All right, so 5 to the negative 1, remember, is a reciprocal. That's 1/5. 5 to the 0 is 1, and 5 to the 1 is 5. So I have my 3 ordered pairs. So let's throw up a nice coordinate system. Let's graph 1/5, negative 1, so right there. 1, 0, right there. And then 5, 1, so right there. And if I connect the dots the best I can, you see, in fact, I do get that nice logarithmic graph. When I say that, what do I mean? I mean, it hugs the negative y-axis, and then it shoots up and levels off as I go, to the positive x-axis. Kind of levels off to the positive x-axis. Well, it's hard to heal. All right? Okay. So you want to stop this and complete the classwork problems 4 through 6. All right. And that's actually the end of the video, so you are good to go.